Yes,
Yeah,
go
I
ahead.
just
pull it up
suggested
and
it
maybe
because
do.
it's just started. So like
Mm-hmm.
it's just started, and plus as well, yeah, like over the past whatever it is, year and a half or whatever, we've looked at like a few medical things and
Mm-hmm.
medical imaging. We
Yeah, in
sort
fact, the
of
one we
know some stuff,
participated
and
in previously was that one too, similar one, right? Like CT scans and stuff.
yeah, yeah, because yeah, like the problem I've had really with like the what do you call it, the bird song one, the rainforest noises. Yeah, like I was trying to do it, but I was competing in like another Kaggle competition at the minute, which is just about to finish, which is like it's like a COVID lung X-ray one. But yeah, like it sounded quite similar to this. But yeah, I was finding it hard, like actually competing in a Kaggle competition at the same time as sort of doing it on another one on the side,
Oh
which is
yeah,
why
that
I,
would
I
be
thought
hard.
it'd be good if we could actually do one that we actually compete in, and
Mm-hmm.
then plus as well you can see how you're doing on the leaderboard, and
Yep.
it makes it a bit more interesting if you're sort of actually sort of taking part in the competition. And yeah,
Yep.
like this one here, there are quite a few other competitions that are similar, so if we like analyze sort of the winning solutions in them,
Mm-hmm.
then we could progress this one.
Yeah, I think one. Yeah, I like the topic also, and the other thing I like about this one is, um, a lot of the, yeah, the CT was 3D, but this one is also like is 3D, but there are different data sets. So um, I think it's how to like in we normally call it like multimodal. Um, so
Mhm.
there's like a MR and PET, but the nice thing about this one is I thought there was one notebook that was really nice. Oh yeah, this guy he's like an official employee of Weights and Biases.
Oh yeah,
Oh
he gave
yeah,
a
he was
presentation to us
Yeah, he
a
gave
month
it.
or
Yeah,
so.
right.
Yeah.
yeah. I really like his notebook. I think that's one I was hoping I could learn weights and like get used like learn weights and biases with this competition. Yeah, so the nice thing about this competition is see this is the same person's brain, right? But we have but they've provided data which is like T1 weighted, T2 weighted, and flare. Um, so these are all MRIs, and when the patient goes in for an MRI scan, they're all taken at the same time. But based on how you set the knobs um, of the MRI scanner, you will get different contrast. So in the T1 weighted, the water is black, right? And so there's some fluid in the middle of the brain, so this water is black. But in the T2 weighted, it's bright. Um, and then flare is like T2 weighted, but they only want to suppress the water only. So it doesn't. It looks different from this one, but this water is. So they have this same brain, but
Sorry, how is T1 and weighted and flare different?
you can see like so this is the white matter here where my cursor is. So in
Yep.
this case,
Right,
the
right.
white matter, yeah, and here it's like much darker. Yeah. So flare is like it's similar to the T2 weighted in some parts, but then all the um, basically the water is distracting. So there's water in two places. There's water in the center of the brain, and there's water in the boundary. So wherever
Mm-hmm.
these little gyri, wherever these little things fold. So and they so normally when we collect these images, I okay, you can think of brain sushi. So this is T1 weighted is like isotropic, so it'll be like 1 by 1 by 1, and flare will be like 1 by 1 by 4. So it's thicker slices, but I didn't check yet what they if they already like they might have already normalized the data for us. But
It seems like the data was huge. I didn't look at it at
mm,
all till today, but the data size seems humongous, right? Like 200 and something odd gigabyte or something.
I thought it was 160.
Oh,
Yeah,
127. Okay.
yeah, yeah. I saw this. Yeah, it's like, yeah, 127. Yeah, and then we have to. Oh, how many image? Oh, they've given 4 images. I see. I thought it was okay. So he just probably.
So four
Uh,
per patient.
yeah, 4 per time point. Yeah. Uh-huh. And I don't know if they have
Oh, time.
multiple. Yeah. Um, yeah, they call it multi-parametric. So this is the first time we have like multiple 3D data sets, right, for each time point. Right.
You have to understand even this whole what's the data and what's the concept, and how they have arranged it and all this kind of stuff.
They basically did it like this, like, yeah, so for each subject you have 4 subfolders, right? And so that way I think they organized it well. Um, the other thing I saw, yeah, would you guys like this competition? I think I like it quite a bit.
Yeah, no, I mean, if two of uh, you have looked at it and stuff, as I said, I'm fairly
Okay.
open to anything, and if there is interest and if it just started and stuff, then that's kind of it's the only um, caveat for me was like, hey, that it's not so compute intensive that
Mm-hmm.
we can't. I mean, because it is so big, it's again hard to deal with. I would imagine to download the data in Colab. I mean, I only have like 100 gig, I think, so
Mm-hmm.
that's one limitation. But I don't have a problem just working in Kaggle because I don't think I'll exhaust the
Yeah.
stuff. But as long as one run doesn't exhaust everything,
Mm-hmm.
I'm okay. That's my only concern and
Okay.
about this.
Okay.
Steve,
I
have
presume,
you tried
yeah.
anything or?
No, I hadn't like really looked that much into it. I just like saw it like it had just started. And saw that it was like sort of pretty similar to ones we'd done before. And yeah, like although like the data is reasonably big, as you say, most of the time recently I've just been sticking in Kaggle and I haven't hit my limits. And plus as well, like
Yeah,
when it tends
yeah.
to be like this type of DICOM thing, people
Mm-hmm.
always produce PNG or JPEG versions, don't they, which are a lot smaller, which
Mm-hmm.
if I need to sort of run things longer, then I can take them over to Colab.
Mm. Okay.
Um, so yeah, not like I'd be
Yeah,
happy
so
to
I
give this
think
one a
we
go.
may, yeah, exactly. We can give it a whirl and see, whether any of those limits really matter. If they don't, then I don't see why not.
Yeah. And I looked at a little bit of things. So I'll just share what I looked at so far. So basically, um, we have like four 3D data sets per time point, and then the goal is to it's like a classification to predict the genetic subtype
Sorry,
of
Mehul, one question. So
yeah
so the structure of the data from what you showed says 0001. So those are patients.
yeah
Where
yes
so each of those in the train, like what we saw are patients, and for each patient there is like four
uh-huh.
types of 3D images. Is that right?
That's right, yeah. Uh-huh.
Okay. And then when you say time point, do you mean within each of those types of images? Those are 3D, so I'm assuming there are slices. So when you use the word time point, now what does that refer to?
Some because normally when we have MRIs, we would scan patients like every 6 months, right? So this is like brain cancer. So maybe they I didn't check the exact data set if they have but basically if you have like if someone has brain cancer, they get MRIs every month, and so you would have these set of 3D images every month. But I don't I
Oh, so
think
you
that
would have four sets of images extending over a period of time. And
yeah.
that's kind of what you're talking. Okay, okay.
Right, but I'm not sure, like in this case, what they gave us. I think maybe they gave us, it looks like they only gave us one time point. Yeah. Yeah. See, this just like one subject and 4 directories, and then, yeah. So maybe they just say, okay, this is just the baseline data or the first scan of the page or whatever, and so we don't have to worry about like any longitudinal analysis.
Yeah, because actually, now that you mention it, in the lung thing, we looked at over time, correct? And we had to predict over time, but here it doesn't. Well, so what is the goal?
Yeah, so basically, when brain tumor is a life-threatening condition, so it's known as a glioblastoma. Okay, and blah. And so if you, but these brain tumors have a genetic subtype. Okay, so if for certain genetic subtypes, you have a higher chance of survival. Okay, so it's like, okay, so if you have this presence of whatever, I don't know the bio, like MGMT promoter methylation has been. So if your subtype is that, then you are okay. You have a better chance of. It's like trying to predict how you would respond to chemotherapy. Okay, so this is kind of this is some of new stuff like, but it's kind of hard. Like to do this genetic analysis, you would have to like drill a hole in your skull and get a piece of tissue from that brain region, and it would take like long time to figure out whether you have that right genetic characterization. So yeah, so in this competition is, can we predict the subtype based on
from the image?
From the image. Yep, that's it. Yeah,
so that's why you don't need the. So what you're trying to detect is the kind of like something genetic or something,
right.
But from images, can you detect that so that you can classify without having to do tissue analysis?
Yep, without having, it's like, it's literally they take a drill and drill a hole in your skull.
Yeah.
It's like, oh man, I don't want that.
Yeah, no, actually, I mean, I like to read medical books and not medical medicine, but people who write about this, and I mean, they literally take a saw to your skull when they open it up.
So I thought I looked at one notebook so far, basically his the EDA he made, and he's been updating it like regularly, so it's nice. He's been adding more and more stuff. So basically, he's just explaining some of the 3 types of images.
I thought there were 4, right?
Oh yeah, sorry,
Is that
4.
the
I guess
one just the base?
Maybe I'll find out more about that and just put in the chat like what are the 4 types. Sometimes they sometimes they do something called contrast weighted. So you would have a T1 weighted image, but the contrast agent can go into where the tumor is. So it will only it will only light up the tumor. So it's easy to see the tumor.
In each of these images, are they taken at the same time? Is it just exactly the same image and then they've just processed it differently? Or are they taken in 4 separate scans?
No, it's you like I've had a T1 weighted image when I was in university. So you just go in the scanner and you sit there, and the modern scanners are pretty good. So you can get this image in like 5 minutes. So they just tell you lie still in the scanner. This takes 5 minutes. This takes maybe 10 minutes. These are the 4 that we have. So we have a flare, we have T1 weighted, T2 weighted, and this is the post contrast. So when they finish the first 3, they may say, okay, now we'll inject. They inject a dye in your body, and then you wait for like whatever, like 10 minutes or whatever. So you wait for some period of time, and then they scan again, and so the dye will go to the tumor and so on. Oh, nice. Okay. So you, when you, so these are the 4 we have. and it's not nothing magical. It's just like, I think when you look at the T1 and T2, you immediately see, right? Like, yeah, if you like, yeah, there are um, it shows different regions of the brain. So, um, yep. And then what does he say? Okay, great. So we have 585 patients, and he says we can there's no, yeah, there's only one time, so you can consider them as independent cases. So that's great. I see.
So it's even a question, open question in a sense of, do we need all four types, or is any one or combination of types more predictive of what you are after?
Yeah, exactly. Yep. You hit. Yeah, exactly. Yeah, we don't know even if we need all four. Like, yeah. And it looks like, I thought it would be more categories, but it's just the MT values, either 1 or 0. So to the presence of that genetic promoter or yeah.
So it's almost like they're looking for one particular whatever it happens to be, and the goal is to detect its presence from images rather than from tissue samples.
Yep. There was yeah, he has some, yeah, he already did all this stuff, right? Like how many subjects. It's pretty, yeah, 307 have it and 278 don't have it, so it's a balanced data set.
Of the number in our training set.
Yeah, it's just, I think its training set feels a little small compared to our previous competitions, but
yeah, but even in general medicine, things seem like the training set is a lot less typically than what you see anything internet related, right? Because you can't like easily get same set of data for more than 1,000 patients at most.
Right. Yeah.
Does it say anything? Normally in the discussion section, it normally says about if you're allowed to use external data sets, or normally you can like use publicly available data sets, which a lot of people would do to sort of increase their number of samples.
Yeah, that's true.
And like also normally in the discussions on a new competition, somebody comes along and like lists all previous competitions that are similar.
That's similar, yeah.
Because I can't remember what competition I did, but I've definitely done some brain one before.
Yeah.
But yeah, like it obviously wasn't looking for like this MGMT thing, but
yeah, I think you're right. There's the medical conference is called Mikai, and they've had like this brain tumor competition from like maybe 2015 or 16.
Right.
So they should be, we should be able to find some data. And what is he trying to? Yeah, he's just going through the like, yeah, what is MRI, blah blah, what we're trying to look at. So I thought, yeah, this notebook is...
sorry, one question, Neville. The lung thing, that lung competition stuff that we saw here, was that also MRI or was that CT? And are the two, and from a purely image perspective, do you know how they are different or whatever?
Yeah, sure.
Was that also MRI?
No, that was CT. And so CT is like very, like CT is little easier because maybe let's go to this. You can think of CT as a 3D X-ray, right? And
right.
The one of the differences is that the intensity values in the CT images have meaning. So let me see. So it's something called Hounsfield units. It's just a term, and so basically, that is. Why is there no?
I recall that. Right, we had to kind of. It kind of shows you the contrast, and you can select that and or like vary it and all that kind of stuff.
Right. Yeah.
post
And
taking a CT scan. It's not, I mean, within the range of what the machine does, you can vary it post capture, is what I recall.
yeah, right. And even you can change the contra window level and all that. But the like in CT, like if you get a CT from London and you get a CT from the US, and you see a value of -1000, so that denotes air, and then greater than water is 0. Okay, and then soft tissue like kidneys and abdomen will be some value, and then bone will be greater than 1000. The problem with in MRI, this we don't have this. We don't have we cannot say like a MRI value of 10 is or any MRI value corresponds to air. We don't have this standardization, so we need some image normalization.
I see.
I think
And what are then the DICOM slices or whatever? Then what are those things? Are they still 3D like slice of the brain, or what is each one then?
exactly.
Like,
It's just a slice of the brain, like and normally it's acquired in axial format. So one sec, let me start something in the background, then I can let's go in. It's you basically want to cover the whole brain. So okay, my more food and food. Okay, it's like a slice of you can go from the around the neck to the top of the brain, and you have axial slices. So if I don't know if I think he did an animation somewhere. Let's see.
Yeah, see his next title down is animate MRI
Oh,
scan.
oh yeah, visualize, create a GIF. Ah yeah, there we go. Okay, so basically, if I just pick one, if you see this, or if you see the first one, it's going from the bottom of. Uh, we are just scrolling through
kind
the
of from
brain.
the stem
Yeah,
all the way to the stem of the brain to the top of the brain.
yeah, exactly. Yep, that's it. And mostly, so normally you see this funny looking thing here. So normally we scan axial, like it's like the engineering drawing when we had in engineering, like is it the top view, side view, or the front view? So normally we scan in axial because but some scanners, I think that is something to dive into, like so that information is there
So
in the
axial
DICOM.
would be top view
Yeah,
or the bottom view.
no, yeah, it's like top view, and then sagittal is the side view. So if you cut the brain in the wait, once let's say, please,
Sagittal is kind of from the ear looking in from the sides.
yeah, from the sides, right? Yeah, yeah. So these are the planes. So that's the axial, and like you said, side.
Oh, coronal is front.
Yeah,
Like coronal is face, sagittal is ear, axial is neck up.
yep. These three planes, and then you can always once you doesn't matter how they acquire the data, you can always convert it by just um, you can convert axial. Okay, it was acquired in one way, but you can convert axial to sagittal or sagittal to coronal by just doing like a very simple matrix multiplication. You just shift by one in the matrix, and then you can get it. So I think one thing
Basically,
that
like a augmentation kind of matrix mapping of coordinates.
yeah, yeah, you can. What else did he do? Okay, yeah, he. This is nice. This is really nice. All this, because always when you have this data, it's a pain to visualize it. And now he has this really nice way to. He probably has the code too, right? Yeah, somewhere.
Yeah, is this where he's putting all the images back into weights and biases? So like it's just a screenshot out of it.
Yeah. Oh, nice. And I really like this. When you click on something, you can get the bigger. Um,
But
Yep, that's so. I think that's all the. I might even have some real data once it loads.
And how much do we have in like the valid, not valid, but in the test or private and public thingy?
Yeah. Oops, why does it always go there? Submission. I guess I have to download it, right? I can't look at it from.
No, actually, you should be able to see that in like the test, or if you go up to.
I think that this is like a notebooks only competition, isn't it? So like I presume whatever's in the test folder there is just like a sort of small sample because it's notebooks only. I presume there's like much more when you actually submit your notebook.
Oh, I see.
But I'm not sure if it tells you anywhere exactly how big the public and private test sets are. But yeah, like that there's just sort of a small test set just to confirm that your notebook's running
Submission
okay.
is okay.
I see.
Yeah, it may be there in the discussion. People might have commented.
Yeah. Yeah, and so probably if you look at one, let's see, one notebook, maybe we just look at this guy. So okay, he did as. Oh, interesting. I didn't think. Okay, so he's thinking of the 3D data set as a video. Okay, so get ideas from there. Okay, that's not a bad idea. Like, yeah, you could either. Yeah, it's fun because it's like, okay, do you go with a 3D model or do you do like a 2D model?
Yeah, and video, he's thinking of the space dimension as as kind of the time dimension equivalent.
Right. He's thinking of the z axis as the time, yeah, which is I don't know. Maybe that sounds
interesting.
What did he do? Yeah, I think one
yeah,
tricky.
So he has submitted.
Why he does like?
Is this just not like an earlier notebook that he's used to create those GIF images?
You know, he actually did the classification. He did some training.
Right.
Oh, nice. Yeah. LSTM. Yeah, interesting.
Yeah, because you have to have the time dimension, and that means you'll have to have a sequence thing, right? That's why he has to use an LSTM.
Okay.
You could use, I guess, transformer type of architecture.
Oh, nice. Okay. Yeah, and then all the man, this is so nice. Steve, have you used weights and biases or?
Yeah, I've just really started getting into it.
Okay.
But yeah, because I used to use like Jovian all the time for like logging stuff, but like weights and biases is better. But yeah, I haven't sort of used all of the sort of the fancy bits like he does. I haven't used sort of sending in images or notebooks or anything. I've just like it's a really good way to keep track of all your training runs.
Okay.
So I've used it like a little bit.
I see. So yeah, I just thought of one thing. I don't know how he handled this problem. Is sometimes the number of I think he mentioned it here. Let's see. So we have these 4 types of sequences. Oh yeah, that's what see. They don't have this same number of slices. Right? So okay. So he basically did a glob for all the possible DICOM slices, right? And then you can see Flare has 74,000, and it's not as bad as I thought it would be. It's pretty close. I thought it would be like T1 weighted might be double of Flare, but it's like yeah. So somehow there is because you want the same when I point, sorry for, if I put my cursor here, then I want this to be the same physical coordinate in the two images. Otherwise, I might be looking at like white matter and maybe like water in this in this one. So
Oh,
normally,
I see.
yeah.
So you're
So
saying that if the X, yeah, in fact, that I don't know whether did we have to deal with it somehow um, in the CT scan situation too, where if you have varying number of slices, then basically like you said, what you're saying is, the point in your head that you're looking at varies depending on the thickness of the slice,
right, yeah.
which corresponds to the number of those slices that you showed, the DICOM slices. Therefore, you have to have a way of normalizing somehow so you land at the same point across these four methods,
Right, yeah.
if they are not all of the same,
Yeah.
whatever, Z slices.
Right, yeah. So maybe I'll check if anybody. So normally we handle it like this. I'll show you. I think I have one case. Normally we just do like a registration, but I didn't check the discussion if anybody's been doing that for this competition.
What is registration?
It's kind of it's basically like aligning the volume, so they will aligning the volume, so they will like the same x and xyz will be the same physical coordinate. Let me,
Is this what you actually work in, Michael?
yeah.
So this is really easy for you, is it?
This is like the product that the company has, but
Yeah.
it's mostly used for clinical trials. But it's very old. It's like it was developed in 2004, so the GUI is like really crappy.
Right.
But they are much better. They're much better tools. But I just don't. I had this open, so I'm far away from the Wi-Fi. Let's see if it's still. Yeah, we have doctors look at this. Okay, yeah, I think this is a good example of. So this is the MRI, right? And that's the axial, right? So I'm yeah, I can. So you can see the green line here. So I'm around somewhere in the neck, and then I can just scroll up, and you can see the. Oh, did I miss the teeth? Yeah, the teeth, blah, blah, nose, and eyes, whatever. And I go to the top. So that's the axial, that's the sagittal, going from the left to the right.
Yeah.
Yeah, that's the middle.
And then
So
what are the coronal or something? Was the face,
and
front, nose?
yep. So if you are in coronal, you are other way. So now I'm at the front. You can see the green line here, and now I'm around the eyes.
Yeah.
Right.
And yeah, these images. Yeah. Yeah. So this is the three planes that he was trying to show, and then the last thing is E. So the MRI is 1 by 1 by 1, and the PET is much thicker. So, but now you can see, if you see the eyes and maybe the nose, you'll see they line up in the two images. So this is the PET image. So the colored is the PET, So instead of T1, but I could do the exact same thing with T1 and T2. Pet is maybe not the best example, but before uh, before we did the registration, they were out they were out of place. Like there's some display thing that doesn't. It's supposed to load the. So I need to do like I need to how do I grab it? I don't use it much, so let's see. Maybe with this. Ah, yeah.
I
Okay.
see. So but is it a static thing now? Also, would trying to align two things make it harder to align with a third and with a fourth? And as you increase the number of alignments, would that kind of increase your inaccuracy because you're now trying to align four things, which may not all be, whereas aligning two things may not be as much of an error prone, but aligning four things because you're compensating for three other things compared to your baseline.
Right. No, that's a great question. So normally we pick one of them as a reference. So whichever is the fine. Normally the T1 is the finest. So I mean, like by finest, I mean it has like 1 by 1 by 1. So this will be the reference image, the reference, and then everything is registered to the T1. So it'll be T2 registered registered to T1. Yeah.
Is it different? Are they different because of the fact that they're taken at different Z positions or position? Or is it different because of the fact they've got like different thicknesses per slice, or is it a bit of both?
Yeah, it's mostly because it's different thicknesses per slice. Maybe let me see if I can download one. Just one subject might not take too long. How do I download one folder? Oh, this and
I click it down. Wow. Even just a flare has 400 files.
Okay, yeah. So this is normally like some. Okay, actually, I just need one slice. So let me see. Let me just.
I think that's just saving you the web page. Yeah.
Yeah. Okay. Now from.
Yeah. Oh.
Yeah. I had to. Okay. Click on the slice and then from here. Yeah. Okay. Let's just call it. Let's just take one flare. This was 31. Okay. And I'll show you a free viewer that's also. Just because I could. Before next time, I'll download some of these and contrast. I can type. Okay, 3. Last one. What happened to you? Yeah, we have all these images, but we have no ground truth, so we can't do any machine learning because we are blinded. So that's why I like this competition. They're like, oh, you have the genetic information. It's like gold. Sorry. Oh, why does it? Oh. Sorry, I made a mistake. Oh, they must be organized based on. They might be organized based on the position in the brain. Also, picking one wasn't the good. Let me just pick one more.
Or did you choose one that was at the neck or something? Is it?
Yeah, at the neck or yeah. I picked image 1, which is not a good idea. So there are 378. So so I need to pick around. Let me just okay one. I'd like to pick maybe 200. Fine, I can't get that. This one should be better. Yeah, okay, it's labeled by slice. Why doesn't it show? That's weird. Okay, yeah. So this is yeah. Okay, I see. So basically, whether I use this or you use any viewer, so there's a free viewer called. I think we looked at it a little bit last time. Micron. Uh, I think I should show you in the free viewer too because yeah, I do have it because okay, yeah, it's called micro dicom. Yeah, there you go. Okay, this is better. So it's just telling us it is it's when the scan happened, it's a T2 weighted, and since I only downloaded one slice, otherwise it would have all the slices and it would let me scroll. And
but this seems, is it a axial view?
no, this is a sagittal view.
Sagittal view, yeah.
Yeah. Pixel. Okay, yeah. So you can see it's like 0.5 by 0.5, and so it's 0.5 by 0.5 and then 1. This is the T2 weighted. Maybe I can get one more just to show the difference. We get roughly the same position. What? Oh, that really is. Oh, so I'm not used to this. I always normally I expect the T1 to be more.
Yeah.
Yeah, it's only did I think yeah, it's the same subject. Yeah, it's the same subject. Yeah. Oh, weird. This has 30. I guess because so for me because we are clinical trials, we can standardize everything. You know, we tell the site uh, you have to take 180 slices, right? We can make rules like that, but these are probably patients in the clinic, and then you can't maybe they can't have those strict rules. Okay, let me take number 16 maybe. Save. Oh, okay, it's not a. So this is a T1 weighted, but it's.
But tell me, as you're doing that, a question, just thinking aloud. It it's possible, for example, to predict based on each one of them so that you do not have to do the registration.
Yeah,
and then apply an ensemble of each of the 4 types and ensemble the models and then see whether that predicts and whatever technique, I forget what's that called, stacking or something, where you weight the different things differently and you can maybe dial that up or down to see whether that gives you, and you could take that approach, which would eliminate having to resolve because at the end of the day, you only care about presence or meaning the 1 or a 0 and not where or anything like that.
Right. Yeah.
So then you don't have to deal with this problem of aligning coordinates.
and
am I right in thinking that? Is
No,
my
I think
question.
that's a great idea. I didn't think of that because I normally just go to registration, but you're absolutely right. There's no reason you could just have 4 models for one for each type of scan, and then just have some stacking or combination of the models to give the final output. Yeah.
The MGMT thing that they're looking for, is that part of the tumor? Is it only in the tumor, or is it in the brain?
That's a great question.
Do they actually give you each of these scans of a brain? I take it like each of these brains has tumors in it somewhere. Do they tell you where the tumor is, or do you have to find it?
They don't tell you where the tumor is. They just tell you. Yeah, they just tell you like they only tell you 0, 1. But yeah, you're right. I don't know if all 585.
No, but zero also, Mehul, doesn't imply. In fact, there are two sets of questions with Steve's comment triggered or question triggered in my mind. One is, to your point, 0 or 1 doesn't imply presence or absence of tumor, because even the 0 means it might mean that they still have the tumor. It's not just that particular genetic marker, right? So that's one thing. Would you agree?
Yeah, I agree. Yeah.
Okay. And then the second part is, I was just thinking again to Steve's comment made me think that I guess they may mention it in the data or whatever, but wouldn't you ideally want to, if you are developing something, I don't know, whether you would want to mix in some scans which do not have any brain cancer at all, in order to make sure that it's not somehow, it's related to Steve's question, that somehow it's not capturing things that are irrelevant to the tumor. If, and this is where it's linked to what Steve said, is if the presence or absence of that marker is independent of whether you have the tumor or not. If it is dependent on having a tumor, then you would think that all the scans would have to be ones that have the tumor, right?
Right.
So that's an excellent question, is whether the marker appears in a brain independent of whether the brain has a tumor or doesn't have a tumor.
Right.
Or is it relevant to the tumor, therefore it only appears when there is a tumor? And then the question that Steve actually asked, which is the thing marker present only in the tumor?
I see.
Because then that might also, and maybe Steve, were you thinking that might tell us which slices to pay attention to even within each of those images, because it could be bounded by the presence or absence of the tumor?
Yeah, I was wondering if they gave you a separate data file to tell you where the tumor was, and then you could only look at those ones rather than examining the whole brain, but perhaps they don't. But yeah.
Let me look at one. I think I'm thinking like they all have tumors, like they all have, and then we just have to find the subtype of whether they have that genetic mark. But yeah, that's to be verified.
What's in the training labels file?
It's just 0 or 1. So
is it?
Yeah, it's just like that. Yep.
All right, so they don't give you any other information?
Yeah, that's it. It's like, you have that genetic thing or not, like.
Yeah.
And normally, if you wanted to see the tumor, it would be most visible on this T1 weighted contrast. This is another funny thing that, see, the T1 had like 32 slices, right? But this one, maybe they care more about the tumor, so this one has like 100. How many slices does this guy have?
Yeah, one of the other ones you looked at had like 400 or something, didn't it?
Right.
Was it just the same patient?
Yeah, same patient.
Oh, Flair.
Yeah, Flair had a lot more. I think this is happening. like in the clinical trials, we can force them to do things more standard, because we are looking at early Alzheimer's. But this is probably from some clinic you don't have time to, and they are probably from different countries, or at least different states in the US. Or I don't know how they collected it. So different hospitals have different scanning. Let me just take one of these. 30, 40, yes. Yeah, let's take maybe 60. It would be nice if they did previews.
Yeah.
Yeah, see, this is with the contrast of if now it's, and this is a coronal. Interesting. Yeah, I think it's going to be really hard to combine them. We might have to do like the number of, because normally the registration works if it's not too different, like the number of slices. In this case, it's just uh, like
Yeah,
30
that's why I'm
slices.
thinking that why, or I was wondering whether we could just develop a model per image type and then combine them, stack them as needed to get the.
We might also have a problem, like if we just take all the flares from all the patients, they might have different number of slices, but that's an easier problem. Like maybe like the LSTM takes care of that, right? For example.
There you might need to pad.
Pad. Okay, I see. Okay.
And ignore the ones where you padded.
Okay. Yeah, but that's so this one, wherever the tumor is, wherever the tumor is, you would see what you see in the it will look like this. But this would you would only see it in the contrast image, and it's
that's a tumor there, is it? That white bit?
Yeah, the whole thing is a tumor. Yeah.
Right.
Yeah, it's pretty scary. We don't do
watching these things can creep you out.
Yeah. Wait, glioblastoma MRI. Yeah, that's the tumor. That's you can. Yeah, it's scary. It's that one. Yeah, sometimes glioblastoma wild type. I think the data set there's enough diversity, and like enough different things to just I just showed you the data, and you came up with the idea for 4 models. Like so I think there's a lot to learn, like maybe what to do with different number of slices, LSTM or non-LSTM, or like a 3D model, 3D kernels. Yeah, all of these. And I know there's generally like a lot of interest. So for example, NVIDIA has this open package. They've been it's from NVIDIA and King's College London. They have these like a PyTorch package for analyzing these data sets. So I think like they have a 3D classification model, and then and then this is active research. I think they just released version 6 like a few days ago, a few weeks ago. Okay. Okay, I think that's I had for now.
Cool. I mean, at least the challenge seems to be in all of the data, right? Meaning the actual eventual prediction task is yay or nay. It's binary. So
yeah,
it's more like how do you deal with the data and get it into, and do you, like you said, what kind of model structure do you want to use to extract?
Is there much
Then,
difference
you
then
know, you
between?
could.
Is there much difference between CT scans and MRI scans?
Yeah, you can. So, like in CTs, because they use X-ray, so the idea is simple. So if if the X-ray beams pass through the bone, right, you will it will the bone will absorb the X-ray. So and on the film you get a white image of the bone, and the air basically doesn't absorb the X-ray, so you get a white you get black. Okay, but MRI is very different. So um, yeah, it's like like MRI physics is so X-ray physics is like okay, like one day lecture, and MRI physics is like a semester of like because they are looking at proton density in the brain. Okay, so there's no radiation, so that's why MRI is also a little safer than X-ray. So um, and they're looking at uh, mm, uh, proton, yeah, proton densities, uh, but you need a very strong magnet to do it. So you might hear things like a 3 Tesla magnet. Uh, um, yeah,
So it's the resonance of what you have in the body to the magnetic field, something,
yeah,
something.
yeah, yep. It's related to resonance. Yeah, and they have these gradients which will like tip the resonance. So it'll make a 90-degree tip, and then they wait for it to come back. Yeah, it's kind of hard to.
But I don't know anything about it, but other than, is it true that the processing that needs to happen for MRI scans is much more involved than what, like as you said, because the CT is essentially an X-ray in 3 dimensions, that's not as much, or is it like, comparable and doesn't, forget the understanding part, but just I'm talking about
Yeah,
taking the data and then.
I think when the scanner collects it, it's in the Fourier domain. So then they have to do like an inverse Fourier transform to get to like an image like this. Um, and in the CT, it's a back projection, and it's like it's another. It's not as complicated as I think as the MRI. The CT processing is simpler. So that's why, for example, anytime a patient gets a stroke, right, when they rush them to the ER, they will never take an MRI. You don't have that much. You don't even have 5 minutes to get set up the scanner, put the patient. They just take a CT, and they will, because they just want to see how big the stroke is, right? How big the damage is. So uh, another difference you can think of, if you see this MRI, this is like exquisite detail here, right? Like um, there are just three things. There's this water, the white matter, and the gray matter on the boundary. So it's like um, so this one block of white is like thousands of neurons, which are like the basic building block. Okay, and they have a head and they have an axon. Um, so normally the on the outside is the neurons, and then you have this anything gray here is like cortical is called gray matter. So normally the three things we hear is gray matter, white matter, and then the CSF. That's the water. So CT cannot give you any of this detail.
Gray matter, white matter, and no matter for
yeah.
For,
Yeah. I think I might have a CT. No, do I have a CT?
But both MRI scans and CT scans, you can like bundle them up into DICOM images. Is that right? So you can handle DICOM. It doesn't matter if it's MRI or CT. DICOM sort of bundles it up, and so you get like the 3D structure from either of them.
Yeah, exactly. So like how in regular images, like JPEG is a standard and PNG, PNG is the standard. So for all medical devices, the standard is DICOM.
Yep.
So yeah, the manufacturer is required to follow the DICOM standard, and yeah, you basically slice. It's normally slices, and most of the data is like one image corresponds to one slice, whether it's brain or knee or whatever.
Yeah, I was also thinking I should poke around because the FastAI repo also has he never covered it in anything, but he has some notebooks that are focused on analyzing DICOM. I don't know whether he's focused on CT or MRI, but I think that would be worth a look.
I see, yeah.
Because he has some notebooks dedicated to, and because in fact he even has a startup focused on medical imaging that he is no longer actively involved in, but he was the founder.
Oh wow.
Then he was.
Okay, I think this is a CT. You'll see the difference immediately. Like, yeah, he's just like. So this is probably this is the bed the patient was lying on. And
right.
yeah, and you can see the bone, the outline. So if there was like a tumor or like a stroke, you could see it very easily. But compared to the MRI, there's nothing, right? There's no detail. Like yeah, you can see the eyes and
in the non in the fleshy part, other than the bony part, it only seems to be able to distinguish. But then again, isn't that though, as we covered in the other thing, a matter of the setting of the Hounsfield unit? Like you could play with that and then make things show up. I mean, maybe not to the same degree of clarity as the MRI, but at least better than it is in this image.
No, it can't differentiate because it doesn't, like the tissue inside the brain doesn't have any properties to give you different Hounsfield units. So I'm trying to adjust. I'm trying to adjust the contrast, but it's really hard. See, it just
so everything is kind of similar in range, so you can't distinguish.
Right. If you when I move my mouse, if you see in the I don't know if you can see the bottom left corner, with the Hounsfield units will appear. So when I'm in the bone, it's like 961. When I'm outside, it should be, it's almost minus 1000. But inside the tissue, see, it's like 38, 43, 36.
Yep.
And yeah, it just can't. So like for all the Alzheimer's trials, we always use MRI. And let me see if I can put them side by side. Oh yeah, cool. I have. Yeah, this is the same person, so this is even better. Oh, but 540. That's weird. Let's see. Maybe it's. Maybe.
So do the radiologists are the ones who learn to read this, or is this something that like any surgeon or any like, since you mentioned knee and the brain, like any surgeon who operates on a part of the body would have to learn to read both MRI and CTs of that part of the body?
Yeah, there's it's mostly radiologists, but then the doctors, they need to understand, like, okay, this is T1, this is T2. But I know, like, but it becomes very complicated. So like we have like, so we want to say, does this brain have Alzheimer's or not, right? And we get we have neuroradiologists. So they are radiologists who have specialized only in the brain, and they train forever. Like maybe they train till they're 40 or 45. And then there are, normally in the ER anybody can read a CT. Like I don't have a CT with a tumor, but if there's a tumor or a stroke, you can see it very easily. So this is a normal CT. Right? So you just see the brain, you see the skull. I don't know. I don't have a way to suppress the skull, so we could see inside a little bit. But let me show you one with. Yes, I'm sure.
Yeah, because like at least my experience with when patients in India, they send you to a CT scan or MRI facility, and then they take it, and then they write a report, which then the heart or the bone or the whatever person then like kind of looks at the report and based on that prescribes a course of action or something.
Yeah, they probably have
like it's a specialized.
Yeah, I think they have like general radiologists and then specializing like in different things. Yeah, probably like neuroradiology, and they probably have musculoskeletal radiology and like lung radiology and stuff. So see, this is a stroke. So you don't need an MRI to see this, right? You're like, okay, this is like shit. Like you okay, you have to rush they have to take immediate action to. It's probably like some blood vessel broke in the brain, and this is like a big. You don't need an arrow to tell you it's.
Yeah.
It's like. Yeah. See. Oh my God.
Yeah, I had my dad's CT from when he had a stroke.
Okay.
I have it, but I haven't been able, or just give me idea to upload it.
Yeah, you can just see it. And normally if it's like.
What was the name of the open source or thing program that you?
It's this microdicom.
Microdicom. Okay.
Yeah.
And it's available. You can just like download and
just download it for Windows. Yeah. Mm-hmm. Yeah. You can download it, and even if you download a few images, you drag it, you should be able to see it. Yeah. Yeah, that's so. See, I don't know. I never remember it. It's just so much. Yeah, you start.
Yeah,
it's
hopefully
like
we
all
don't need to know that
quantum
bit.
mechanics.
Yeah.
Yeah, we don't need to go there. Yeah, it's like these are without
it's
the magnetic.
You take a picture and electrons are spinning and magnetism happens, and lo and behold, you have an image.
Right. Yeah, so I think, but this so normally the protons are like just like just floating around doing their own thing, and you apply a strong magnetic field, and they all get aligned with the magnetic field, and in one you see most of them are pointing up, but there'll be a few pointing down. So I think it's something like you have 1 million pointing up, and maybe 1,000,006 pointing down, or it's a very small number, like. And then you apply an RF pulse to flip them like that, and then you.
Mehul, you're like depressing us by showing that kids are supposed to be understanding this.
No, not kids.
Kids, frontiers for young minds. It's like we have old minds.
Oh my God, I didn't see that. Wow.
It says kids, and I'm like, if kids understand this stuff, then I just give up.
No, I can't. Why did they? Wait, who wrote? Why did they write it for kids, for young minds? I don't know. I think nowadays kids are like too smart. They can. See, I like this. Oh my God.
I want to show this to my kids. I'm not sure they'll be very happy about it.
Yeah, I mean, that's just. I just saw that. That's too much.
Oh my God. Yeah, I didn't even notice that. Yeah, that's pretty much.
It's a good explanation. So I guess if you really want to get a kind of like a base level understanding, would be a good thing.
Yeah. Yeah. How do you get image from these? But yeah, that's.
In terms of the competition, you can go back to the actual competition page and just look at the discussion bit of it.
Okay.
Yeah, their discussion beside it.
Oh, nice. See okay, somebody's already converted to
PNG. Oh,
PNG.
5.2 gig. Oh, cool. 5 gig is
Okay,
handleable,
and
right?
this is what um, you were saying,
He was
right? Somebody's already compared, like made a list of all the
Yeah, they
data.
normally go through and sort of see which competitions were similar in the past or whatever.
Okay, cool. Intracranial hemorrhage. Okay.
Yeah, that's like would entail probably like what you showed in one of those CTUs and stuff,
Yeah.
right? Like,
Oh, I remember this competition was crazy. It was CT, and it wasn't MRI, but even CT can have many subtypes. Okay. So you can have like yeah, some stroke might be more serious, right? Oh, I remember when this guy came up with a solution. I thought it was very clever because I thought it'll be 3D model, but like it was the sequential models that won this competition. Like I think in the top 10, maybe 5 or 6 of them were sequential. So that was amazing. Yeah.
yeah, and I was just, I mean, again, just throwing initial reactions without too much thought is, one ensemble is ensembling the type and then kind of doing that. And then for each of them, each of the types, you could potentially have varieties of sequences of sequence
Hmm.
models. Like in what I mean is, one model could be using LSTM, another could be using attention, and you could potentially kind of like ensemble them too.
Okay. Okay. Yeah. Oh, so they have papers, nice. And then what else? Oh, okay, previous brain tumor data sets.
Yeah,
Yeah.
data set.
Prior research. What is the
Oh,
what the
pre-trained 3D CNS.
oh wow.
Pre-trained 3D CNS.
Oh wow, that's pretty cool. Yeah. Oh my God. I see this is pretty big. Yeah, this is a pretty big area, so that's why there's so many.
Yeah.
Wow.
Uh,
Yes. Yeah, this guy is really good. So he's a grandmaster, but it's I feel ashamed because he's a doctor.
Is it?
And
Yeah.
and he's so good at coding. So I'm like, oh my God. This is
yeah, he's a radiology resident, right? It's a
yeah, I'm telling you, this next generation is like, oh, we can do medicine and
oh
it's
yeah, I
really
mean that's in fact um, some of these, especially in the medical domain, it seems nowadays um, in some fields, I'm increasingly seeing the top guys do combination of doctorate and MD because they, when they're doing MD, they do so much individual like clinical research or something that
Mhm.
publishing it in a kind of a PhD oriented program seems like there's not that much incremental work. Invariably, like you look at any of these top schools,
Mhm.
Stanford, even University of Washington, medical school, any good medical school, many of the graduates seem to like come out with PhD MD combos.
Mhm. Mhm. Yes, I
One
see.
would think doing one would be hard enough, but
Yeah. Yeah, see that's the competition I was telling you about. Like it's the brain. It's called BRATS. So it's been so he uploaded the data sets from the previous editions, and
Right.
oh, there's an ongoing yearly thing.
yeah, yeah. It's a pretty big problem with a brain tumor. Like it's because just the prognosis is so bad. Like especially like you're fine one day and suddenly like you have so there's a lot of interest as you can see like um,
Yeah, and sadly, I know of at least two people to whom that happened. I mean, perfectly
us.
healthy one day and then
Yeah,
diagnosed with, and they're just thinking, oh, I'm just having this minor problem, and it's like
yeah.
very tragic.
Hmm. Yeah, okay. Yeah, and we have time, right? I think yeah, that's what yeah we have. Oh yeah, a lot of yeah. October
Yeah.
15th
So I think
is
it did
yeah.
start, yeah, 18 days ago. So
Okay,
Yeah, it's like sort of 2.5 months left.
Yeah, I think that's a good time. Yeah.
Yeah, like it's good to come in. I think after a couple of weeks, like after a couple of weeks, people have done all the
Yeah.
EDA stuff or whatever,
EDAs,
and you don't have to do it
right.
yourself. Yeah.
Right.
So,
Even understanding, I think this helped quite a bit in getting, a baseline of understanding of MRI versus and what are the four types and the fact that they're all not of the same slices aspect, and so this is excellent groundwork.
Yeah, so he's I think he's done a whole notebook to okay, there you go. Yeah, so he's oh nice. He's probably trying it per subject. How is it? Yeah, see, the T1 is mostly axial, that's what I expect. But I'm just a little like the flare is like has a much bigger mix of okay. He didn't he just and I have time to commit, so I can I should be active in this.
At least I'll do a little bit to understand the data and just look at the EDA type and see what's the simplest thing to do.
Yeah, I'm really interested in the sequence, like if like is it like a 3D model going to win or like a 2D plus sequence modeling? But that really surprised me in that CT competition that out of the top 10, so many were sequence models. Let's see.
Yeah, so the sequence dealt with the same thing as here of slices, correct?
Right. Yep.
That kind of makes sense if you are not, this is exactly what he's doing when he says video too, right? He's just handling it as a sequence. He used the term video, but it basically is a sequence. Right. So, yeah, you would have to come up with some kind of sequence to deal with the Z-plane thingy, unless I don't know what this 3D convolved thing is.
Yeah, I think the basic idea is you basically have a 3D convolution filter, but I don't know the details about like how you account for all the different all the different sizes, in the X, Y, and Z.
Yeah, I've just been reading the book. I'm not sure if you have it. It's like Deep Learning with PyTorch. The whole second half of it, he sort of does a project, but his is doing like 3D images. They're CT scans of lungs, and it's like looking at nodules on lungs or whatever. But like he goes through all the DICOM images and how you deal with all the sort of the Z coordinates.
Oh, I see. Okay.
Is that the I forget what the publisher?
Yeah, that's the one there. Yeah, so part 2 of the book is like a whole massive project about sort of dealing with DICOM.
Oh, cool! It's free. Oh, nice.
Yeah, no. In fact, strangely, Steve, I was in the early version. I was one of the reviewers of that thingy.
Oh yeah.
And I got in Manning. I'm one of the reviewers. Sometimes I review books, so I kind of said, man, the early part is really good in exposing you to PyTorch. The later part, it just like they had the notebooks available too that you can play with. But at that time I didn't know the baseline of what Mehul explained or even we dealt with. So it was all totally Greek and Latin. I was like, you have to either slice the book into 2 parts or say part 2 is like, dealing with something which is very specialized, because you just get lost otherwise.
Yeah, no, you really need to follow it through. And the only thing I find like is a downside in the second part of the book is the training data is like absolutely huge. And like he's like saying you have to like download all these files, and it's like, I don't know, 300. It says there it was like 220 gig.
Oh my god.
Yeah, so I didn't have that much space, but you can download part of it. But in terms of like sort of explaining DICOM and like making models with 3D CNNs, it's pretty good, and it explains it. Yeah, so like you can see there, he's like sort of got cubes or whatever, where he's taking bits of the lungs and yeah, like using 3D CNN models on them.
I see. Okay.
But like here as well.
Yeah, and the good thing is now I have a motivation to learn it. At that time, I was just going through it because I had to go through it, and it was like, wow, I'm just spending so much time trying to figure out this.
Yeah, because at the minute I'm just like
good.
finishing off. There's like another Kaggle competition that's just finishing off at the minute. It's like it's about COVID, like detecting COVID in lung images. Although it is just it's just X-rays of the lungs, so it's only 2D. But yeah, I've sort of been using the stuff from this book just to help me through it.
Yeah, I can send you my CT scan of the lungs. I took it after arguing with the guy saying, no, I want it, because one day I wanted to analyze it.
Right.
I have the CT scan they took when I got COVID.
Yeah.
Yeah. Nice. Okay.
So there is, yeah, I saw somebody else post too that there is, so it's about to end, and that's from X-rays only, or do they do something else too?
No, it's X-rays only, but what you have to do though, you have to, there's like 4 classifications you got to say. Is it like pneumonia, or is it COVID, or like then there's like a segmentation part to it as well, where you have to like find the bounding area for where the sort of the thing is.
I see.
So he does the same in this book here. So like there's 2 halves to it. There's like a classification part to say which of the 4 things it is, and then there's the segmentation part, and he actually does both of those in his book here. So, but
that'd be cool. I think now I'd be more more application oriented reading. It would kind of resonate more, I think.
Yeah.
So for this competition, you are using PyTorch, Steve, for the COVID competition? Nice.
Yeah, I've sort of just try to use PyTorch all the time at the minute, whatever. So, but there's obviously like a lot of notebooks in Keras as well. But but like most people are using segmentation stuff, you know, like YOLO, whatever it's called, YOLO V5, and can't remember the name of the other one, but yeah, so like they're using those sort of segmentation detection things.
Okay, cool. Yeah. Okay, I need to drop off and.
That's a good reference to go through in the background.
Yeah.
Yeah, cool. But yeah, so I'm happy to proceed and join this competition or whatever if the 2 of you are up for it.
Yeah, I think let's just dive into it, and we'll just use this time and.
Yeah, I think that's good.
Huddle up once a week and see what, then if other people join, then, you know, as I said, if they're just watching, then it doesn't matter, and until 5 it doesn't matter anyway. So we can do whatever.
Okay, cool.
Okay, talk to you next week.
Okay, great. Thanks a lot, Mehul and Steve, and we'll talk next week, same time.
Yep. Bye.
Bye.